Here we need to bring together what we know from the previous two exercises, namely, first of all, that we know what the variational formulation is of a generalized eigenvalue problem, and B, that we know what the generalized eigenvalue problem for the electric field looks like. So pause the video and see if you can combine these two pieces of information to derive the following variational expression for the electric field. Let's have a look again at the puzzle pieces that we have. So we had an operator A that was curl, curl, and then we had an operator B, which was multiplication by the permittivity. And together they formed a generalized eigenvalue problem for the electric field, like so. So A operating upon E gives us back B operating upon E, but multiplied by an eigenvalue, which is lambda. In our case, lambda was omega squared mu, but that's not really relevant in this case. We also know that if we have such a generalized eigenvalue problem, that the corresponding variational formulation is equal to E A E divided then by E B E. And in our case, we know what A and B are. So let's just substitute what we know. So for here we have curl of E, and then for our denominator we have E and then epsilon E. Almost there. What we now need to do is take that step that we've taken many times before in the past. We looked at one of these curl operators here, we moved it to the first factor, and then there's a price to pay involving a surface integral, so which will give us then curl E times curl E plus this surface integral. And again, we're only looking at situations where that surface integral is 0, and then divide that by E epsilon E. Final step we need to take is just reminding ourselves what that shorthand notation here actually is for that scalar product. It's a volume integral of the first factor times the complex conjugate of the second factor. And in our case, they will just combine to give us the squared modulus. So we have the curl of E squared modulus dv. And then we divide everything by epsilon squared modulus of E dv. And again, we can bring epsilon here outside of the complex conjugate simply because epsilon is real valued in our case. Otherwise also the operator B would not be Hermitian. But now if we combine everything, we have indeed derived a nice variational formulation for the electric field.